If we're looking for the ground state energy when the energy in each well depends on the number of particles in that well squared, then it's fairly clear that what we need to do is we need to even out the number of particles in each well. And so in fact, what you tend to get is if you have a certain number of wells and a certain number of particles, a very even division of them between those wells means you've got a very well specified number in each well. In other words, what you get is a number state. So the ground state of the Bose-Hubbard model where you have U much greater than J is where you have a number state in each well, and that's called the Mott insulator phase. So how would you show these things experimentally? Well, it's not too bad. What you do is you take your atoms and you cool them in a trap and you drop them. And if you drop them, what you get on your screen below is a blob. Now suppose instead you slowly shine on a gentle lattice on your atoms first, and you trap them in that instead. Then if your lattice is sufficiently weak, of course, when you drop them, what you get is a blob. But if you shine a slightly stronger lattice, then what you get is you get all the atoms arranged into this regular lattice, and when you drop something like that, it makes an interference pattern just like a diffraction grating. So when you drop that, what you get is you get your central blob, then you also get all these diffraction peaks around it. But as you turn up the strength of the lattice even further, then you stop being in the superfluid regime. And instead of being in the superfluid regime where these different sites have a well-defined phase with respect to each other, you start being in the regime where you've got a Mott insulator. And a Mott insulator has a well-defined number of particles at each site, and so they don't have a well-defined phase with respect to each other. So then when you drop them, of course, what you get is a big fuzzy blob. And that's what you see in these beautiful experiments from 2002, where when they have no potential at all, they just have a blob. And then as they increase the strength of the potential, they get this increasingly well-defined diffraction pattern. But as they increase it further, they get towards this big fuzzy blob. And so they've seen that the coherence has gone away. Now, as a general rule, seeing coherence go away is a fairly bad experimental signature, because it's very easy to do a bunch of things in your experiment and see your beautifully well-developed phase fringes go away. And so there's another extremely good sign that this is exactly the Mott insulator transition and not some experimental error. And that method is to restore the coherence again, in other words, to go back. So the way they make these pictures is they start off with their Bose-Einstein condensate and they slowly turn up the interaction strength. The reason they do that slowly is that they are hopefully, if they start off in the ground state of the trap and they turn on their lasers slowly, then hopefully they should in fact stay in the ground state. If you do anything fast, all you're doing is giving it a kick. But if you do it slowly, then you can stay in the ground state, which is why they're hoping to see first they're in the regime where they should be in the superfluid ground state, and later they should be in the Mott insulator ground state because they got there slowly enough that the atoms had times to sort themselves out into their various number states. What that means is, if they then go back and turn the lattice back down again, they should be able to reform the superfluid state. And if they do that, then the fringes should come back. And so what they did was they turned up the strength of the lattice like this until they got to there, and they held that for a while, and then they slowly turned it back again. And depending on how fast they turned it back again, they either got fringes or they didn't. So if they went back really fast, they just got their big fuzzy blob. But if they went back more slowly, it turns out their fringes came back. So this is just a pretty image of that same data. In this first image here, they have the diffraction pattern they get when they drop their atoms out of the superfluid regime. Here, they have the pattern they get when they drop their atoms out of the Mott insulator regime. So they turn the lattice up so strongly that they're in the Mott insulator state, and then they lose their fringes. And this is the interesting one. This is where they turn up their lattice until they're in the Mott insulator regime, then they hold it there for a while, and then they slowly draw it back into the superfluid regime. If they draw it back slowly enough, then they get their fringes back. And so you can see that you really are changing between the two different ground states of the system and not just accidentally destroying all your coherence. Now, all those experiments relied on staying in the ground state of the system by slowly changing the Hamiltonian adiabatically. Now, you can also change the Hamiltonian very fast. You could flash on a strong lattice if you wanted. And it turns out something interesting happens in that regime as well. So if you started off, say, in a coherent state, and what I've done there is I've expanded out each of the coherent states in terms of the number states. And the reason I've done that is if we suddenly flash the Hamiltonian until the nonlinear term is dominant, then this nonlinear term here is diagonal in number. And so the number states are eigenstates. And so we know that the number states are the eigenstates of the Hamiltonian, so we know exactly how they evolve in time. And so if we take this coherent state as an initial state and we turn on a very strong interaction, then we know exactly what that's going to do as a function of time. So of course all these number states are rotating at different frequencies, but you'll notice that they're all rotating at different multiples of the same frequency. And therefore, there are particular times at which all of these different phases are going to come back and they're going to be back in phase. So that revival time is fairly easy to define, where m is some integer. And we also have a collapse time where that variance in the number is essentially given to us from our choice of coherent states. And of course, that collapse and revival has been measured experimentally, and so they saw as they waited different amounts of times that their interference fringes would come and go away again. And they even found that they could play with and measure the collapse time changing. So that all comes down to the variance in the number. Now for a coherent state, you tell me a particular coherent state, I can tell you the variance in that number. But as you go from the superfluid regime to the Mott insulator regime, we know we're going towards actual number states. And so the variances in the number of atoms at each site is going to change and go down. And they found that as they went towards the Mott insulator regime, if they then suddenly slammed on a really strong lattice, they found that their collapse time changed. So they found it went from collapsing fairly fast to collapsing a little bit slower because the variance of the number went down.